now that we've computed determinants, we might be wondering how we can use them in applications. Some of the most interesting applications are the geometric applications of the determinant. We're going to start by looking at a unit square, which is a square of area 1. I've put it such that one of the vertices of the square is the origin, and then we go 1, 0, 0, 1, and 1, 1. We're now going to look at this matrix M. M is a transformation matrix, and it's 2 by 2. We first need to think about what the determinant of this matrix is, and using the formula AD minus BC, we see that the determinant of this matrix is 6. We need to also think about what would happen if we performed this transformation matrix, if we performed its transformation to our 4 points. Well, if we perform the matrix to the 4 vertices of our square, 0, 0 will remain invariant, which makes sense because this is a linear transformation. We also will have the point 1, 0 becoming the point 2, 0, the point 0, 1 becoming the point 0, 3, and the point 1, 1 becoming the point 2, 3. Well, let's see what that looks like. It's a rectangle with a width of 2 and a height of 3, and thus an area of 6. It's almost as if the area has been changed by a factor of the determinant, which is exactly right. The determinant is an area scaling factor for objects in 2D if we're performing 2D transformations. Now let's take a look at a matrix where the determinant is negative. Matrix M has a determinant of -1. Using what we know about the area scaling factor, it's implying that the area should not be changed. But does the negative have to do anything? Let's take a look at the red image in the middle of the screen. It's a unit circle with an X and an O added for clarity. If we perform this transformation to those 4 important points, the 2 points on the circle, the X, and the circle inside, we find there 4 images, 0, 1 for the point 1, 0, -1, 0 for the point 0, 1. The point half, half, where the circle lies, will end up at -half, -1/2, and the point -1/2, 1/2 will actually remain the same. I always like to be thinking about what transformation is actually occurring. So if this point is moving over here, this point over here, the X staying where it is, and the circle moving, we get that this is the reflection over the line y equals -x. So what's it going to look like after the transformation? We see that in blue, all of the points have moved to their new locations. It's important to also note that in the original transformation, the X was to the left of the circle. But after the transformation, the X is to the right of the circle. This is a concept we call orientation reversing. If the determinant is negative, the orientation of the image will be reversed. This image cannot be rotated to look identical to the original image. If we go back, there's no way to rotate this image to look like the blue circle. You can kind of think about it like a set of gloves or hands. There's no way to rotate your left hand such that it looks exactly like your right hand. They are mirror images of each other. When the determinant is less than 0, the image is mirrored or reversed. If the determinant is positive, we call it orientation preserving. Let's just recap the things we've seen so far in the video. For 2D transformation matrices, the determinant is the area scaling factor. If your original object has an area of 10 and the determinant of its transformation matrix is 4, the new area would be 40. While we didn't explicitly show an example of this, for 3-dimensional transformation matrices, the determinant is a volume scaling factor. When we look at our next video series on applications of the determinant, this will become apparent. It generalizes for four-dimensional matrices and higher that the determinant is a hypervolume scaling factor. We don't need to worry too much about the visual behind this, but it is good to think about the overall generalization, that determinants perform whatever dimension you're in, that type of scaling. So 2D is area, 3D is volume, and so on. If the determinant is positive, we call the transformation orientation preserving. But if the determinant is negative, we call the transformation orientation reversing. Again, it's easiest to think about orientation reversed as a set of hands. There is no way to move the left hand through rotation or translation such that it lies identically on top of the right. A reflection needs to occur for them to match up. Welcome to the Kernel of Truth, a new linear algebra focused math YouTube channel. Make sure you like this video and subscribe for updates.